Okay, welcome to another live session for the online course. It's been a couple of weeks and looking forward to your questions. Floor is open.
So the first question is from a viewer who's on with us live who asks, how did the formation of voids in the universe occur?
So the large-scale structure of the universe, which is the distribution of galaxies in three-dimensional space, is fascinating because this is just a single force of gravity operating over time, and yet it turned the initially smooth, almost uniform universe when it was young and dense and hot into this amazing set of structures on very large scales. And yet it's still, again, a single force responsible for this acting over time. So basically, structure started slowly to evolve. In physics parlance, it would be perturbations, so very small density variations where one region was slightly denser than another. And of course, when the density is higher, the gravity is stronger. And at some point, when the perturbations or the variations in density reach about 50 to 100%, in other words, some regions are twice as dense as others, and all this takes a couple 100 million years, then you have what's called gravitational collapse. The thing becomes nonlinear. As the dense regions get denser, the gravity gets stronger, and so on, positive feedback. And so you quickly form structures in this situation. And the structures, so you accelerate the formation of structures, which essentially clears out regions between galaxies. So that's voids, but it's not obvious that you would get very large voids this way. In fact, the largest structures in the universe are several 100 million light years across. That's far larger than an individual galaxy. And the largest voids in the universe are on similar scales. Structure in the universe is sort of scale-free, which means there's equal amounts of structure on small, medium, large, and super large scales. And the voids just represent the structure, which is to say clusters and superclusters, and then the sort of anti-structure, if you like, which is the voids in between those large entities, occupy very large scales in the universe. We know it's still just a single force operating because if you try and simulate this in a computer, all you have to put in is normal matter plus dark matter, which outweighs normal matter by a factor of 6 or so, and then just let time evolve in an expanding universe, and you generate these amazing voids in a computer just as we see in the real universe.
Right, our next question is again from a live viewer who asks, what causes the variability in variable stars such as RR Lyra stars?
So variable stars are interesting because most stars, main sequence stars like the sun, are extremely stable. One of the misconceptions of stars is that they're bombs because fusion is going on, and the only form of hydrogen fusion we've ever had on the Earth is the horrible destructive power of the H-bomb, uncontrolled reaction. Well, in stars, the nuclear reactions are controlled and the stars are stable. The sun will be stable for another 4 or 5 billion years, same amount of time it's already been living. But not all stars are stable. Some stars, especially late in their lives, and especially more massive stars, have various modes of variability, where the increased rate in nuclear reactions generates more pressure, which puffs the star out, which cools it down, which allows the star to recollapse and increase nuclear reactions again by increasing the temperature. And so you set up a cycle. And there are natural variability timescales corresponding to the mass or the size of the star. And so, for example, in Cepheid variables, this natural variability cycle, or thermostatic mechanism based on instability, leads to a correlation between the luminosity of the star and its period of variability. So the more luminous and massive Cepheids vary on longer timescales. They're physically larger stars. And that correlation was actually used to unlock the secret of the galaxies in the early 20th century. So some variable stars like Cepheids and RR Lyrae are quite regular, and these instabilities occur with a very specific time scale. Other variables are irregular in nature. They're not thermostatically modulated or regulated, and so a nova would be an extreme version of this situation, of where the variation is an enormous range in luminosity and it occurs essentially stochastically, so not on a repeatable timescale. Astronomers have cataloged dozens, I think it's almost 50 different type of variable stars, and each of them represents a different type of mechanism within the star that leads to the fusion energy rate changing over time and leading to potentially a periodic variation or a sort of aperiodic or stochastic variation. And many of these stars are very useful in astrophysics.
Right, the next question is from Angelo, who is on with us live, who asks, how does the migration of planets, in particular gas giant planets like Jupiter and Saturn, take place? Were there any fluctuations of the gravitational fields of the planets?
We know that migration is a common feature of planet formation. It was told to us by the properties of the first exoplanets to be discovered, because the first exoplanets to be discovered in late 1990s were often hot Jupiters. So Jupiter-sized planets far closer to the sun than the giant planets are in our solar system. In fact, the first exoplanet discovered was a half Jupiter mass planet on a 4.5-day orbit, incredibly fast and close. And the reason we know that planets migrate is that there's no plausible scenario whereby in a collapsing rotating gas cloud you can put that much mass that close to the star. So you cannot form these giant planets where we see them now. Ergo, they must have migrated. Now, once migration became an ingredient in how planetary systems form, people realized that adding or including the idea of migration in our solar system would solve some puzzles. And so it's likely, although we don't have decisive evidence for it, that the planets in our solar system changed their positions quite substantially in the first 100 million years or so. And basically, in the first 100 million years of a solar system formation, while the material is still being absorbed into planets and there's a lot of rocky debris left over, the stability is low. There's potential for substantial instability. And in instability, you can have gravitational interactions between the planets that can move them around in their orbits, could potentially eject planets from the system entirely. And so the thing is not very stable at all. Eventually, it will stabilize, and our solar system is long-term stable, won't change substantially for hundreds of millions of years. So how omnipresent is planet migration? We really don't know. It seems to be implicated in at least 10 or maybe 20% of the exoplanet systems found so far. Not just the hot Jupiters, but some of the other systems too. We see the relic imprint of it in our solar system, and so we think it's quite a common feature of planets.
Our next question from Dan, who is on with us live, is space-time massive? And by that, I believe he means, does space-time have mass?
And so that's an interesting question. Space-time itself is a continuum of space and time that are interconnected according to the theory of general relativity, and intrinsically is independent of mass. So the simple answer to the question is no, space-time does not have mass and is not massive. It's just a backdrop. It's just a construct, if you like, for describing how objects are situated in the space and how they evolve in the time axis. So space-time, empty space-time, of course, can exist hypothetically. And so space-time could exist in our theories of physics without any reference to mass or energy. So definitely you can imagine space-time where mass is not attributed at all.
Our next question is from a live viewer, Kushal, who asks, what are baryonic acoustic oscillations and how can they be used for finding distances?
So Baryonic acoustic oscillations, abbreviated in the research literature as BAO, oscillations or variations, are an interesting phenomenon whereby in the early universe, when the universe was young, at about the era where we see the microwave background radiation, so that's when the universe had a redshift of 1,000 and was 400,000 years old, the dark matter and the baryons, which is the smaller amount of normal material that we're made of and all stars and galaxies are made of, they were coupled with radiation in this early universe. And so you can essentially get resonances in the interactions between photons and baryonic particles in the expanding universe. And those resonances, of course, are associated with the scale of the universe at that time. So those resonances are essentially a telltale of the scale of the universe very early on. Now, as the universe evolves, as matter and radiation part ways, which is what happens after 400,000 years after the Big Bang, it's called decoupling, or when the universe becomes transparent, then that imprint that was present in the early universe of the baryons and the photons in interaction and being coupled doesn't go away. The relic of that imprint just dilutes with the expansion of space and the passage of time. And of course, the scale of that extends with the expansion of the universe. And so in principle, if you looked in the present day universe at galaxy structures, you can see on very large scale this coupling, a relic of this coupling. And essentially it means you have to look on scales of a few 100 million light years. You're looking essentially for excess correlation between galaxies. Any two galaxies a few 100 million light years apart should not be correlated at all. I mean, in conventional astrophysics, there's no reason they should be aware of each other's existence or have any excess correlation above random. But if the BAO in the acoustic oscillation scenario, then they will have a very slight excess probability on a particular scale corresponding to this resonance scale early in the universe. It's a very subtle signal, and you need samples of tens of thousands of galaxies to detect it. And pleased to say, one of our faculty, he since moved to Harvard, but Daniel Eisenstein here, one of my colleagues, when he did the work, was the first to use the Sloan Digital Sky Survey to detect this BAO, or Baryonic Acoustic Oscillation signature. And it becomes a very useful metric in testing the Big Bang model and in testing our measurement of how much baryon component of the universe there is. Because it's a measurement made at the present day, which you can then compare to measurements made in the earlier universe through microwaves. And so you have a sort of check on the model and a baseline on the model. It's hard to do much better, and so big surveys of hundreds of thousands or millions of galaxies allow, in principle, even better measurements of this effect. And quasars have been used to try and measure this effect, quite rare objects, but sampling these large scales. So it's a sort of niche area of cosmology, but quite an important one.
All right, our next question is from Richard, who's on with us live, who asks, why is there such a heated controversy between some of the planetary scientists about whether or not Pluto is a planet? Does the label really matter, or is this a minor taxonomic issue?
To many people, it is taxonomic. It's sort of being pedantic and splitting hairs. To most astrophysicists or planetary scientists, it's really not a distinction that matters very much, whether something is a planet or a dwarf planet or what you want to call it. What just matters is whether you can understand its properties and its relation to other objects in the solar system. So in that sense, it really is just pedantic and semantic. I think the reason it's come back into the news is there's been a couple of papers arguing quite strongly that astronomers, when they voted down Pluto a few decades ago as a planet and demoted it to a dwarf planet, were being historically inaccurate, because the criteria they essentially used to demote it was the fact that Pluto was not massive enough to have cleared out its orbit as all the material in the solar system was forming objects. And that was sort of invoking a criterion that has not been consistently used in other planet definitions over the last century. So this argument has been made that there was an anachronistic or inappropriate criterion applied to Pluto to demote it, and that if you took that away, the most intuitive and logical criteria for a planet is just something that's massive enough to be round by its own gravity, and Pluto clearly fits that bill. So there's a counter argument, and in fact, there's probably going to be some push to reinstate Pluto, and there may indeed be another vote in another IAU meeting. The status of Pluto in that way is a semantic detail. It's also probable that there are several objects bigger than Pluto in the Kuiper Belt, outer solar system. So for consistency, if it was based on size, you would have to include them as planets as well, which is part of the reason why astronomers wanted to demote it.
All right, the next question is from Will, who's on with us live, who asks, in the cosmological heat death scenario, everything just cools down. Where does the heat go? Normally, for instance, a cup of coffee cools down and the room warms up.
Right. So in normal thermodynamics, you have a closed system. You have a room or a planet atmosphere or something where the heat flows and you can follow the heat and the radiation and see what's happening. The big difference with the universe is is expanding. So in the heat death scenario for the universe, as objects cool and as the sources of fusion die out and eventually there are no stars creating new energy that way, it's all happening in the context of an expanding universe. So the radiation, the leakage of radiation into space is into an expanding space-time where the expansion itself adds a further cooling effect because stretching the wavelength or stretching the space lowers the energy of the photons that fill the space. So that's really what causes the heat death, and that's why it's not subject to a simple thermodynamic calculation, because the normal thermodynamic equilibrium in a lab experiment is subverted by the fact that the universe is expanding. Moreover, the universe is expanding at a more and more rapid rate because of dark energy. So this is a very strong effect, and it leads very rapidly, and really in a few billion years in a accelerating universe scenario, to the heat death.
All right, our next question from a live viewer is from Steve, who asks, is there any relationship between the first general population 3 stars and black holes found in most galactic centers?
Yes, there could be. It's a good question. So for terminology first, population 3 stars is a term astronomers invented to talk about what they think is the first generation of stars in the universe. In the sort of bottom-up formation scenario of structure in the universe, it's likely that stars form before galaxies. And in the very early universe, when it was dense, it's likely that the most massive stars were much more massive than the most massive stars we see around us. For instance, it's very hard to find any star in the Milky Way that's more than 100 or 120 times the mass of the sun. In the earlier, denser universe, it's speculated that the most massive stars could have been a couple of hundred solar masses. And when those die quite quickly, quick lifetimes, of course, they will leave behind pretty massive black holes, maybe 20, 30, 50, 70 times the mass of the sun. And those black holes of that size form fairly quickly in the early universe are excellent potential seeds for the black holes that we see at the center of galaxies now, because in the earlier, denser universe, as galaxies are first starting to form with these pretty beefy stellar black holes at the center, those black holes will double in mass or size quite quickly, and so they can plausibly ratchet up in mass from hundreds through thousands, tens of thousands, towards millions of times the mass of the sun. So the population 3 scenario of including a significant population of fairly hefty black holes it's quite plausible as a basis for where the black holes in the center of galaxies came from and how they started.
All right, the next question from Tom, who's on with us live, is space expanding? If we think it is, could our space be expanding as well, so that a 1 meter ruler could be getting larger and we could never tell?
Interesting conjecture. And so, yes, since space is invisible, it's always a good question of what is exactly expanding. So expanding space is really only manifest on large scales, which is to say larger than a galaxy. Galaxies themselves are held together by their internal gravity, and that's essentially dark matter, which dominates normal matter. So galaxies, as we can measure, in fact, we don't have to guess, are not, we believe, getting larger over time, even though they're moving further and further apart, faster and faster by the accelerating expansion. So gravity retains control or controls the size of objects like galaxies and certainly stars and planets. And then solid objects like planets or rocks or rulers are held together by much stronger forces, by interatomic or molecular forces. So the integrity of solid material of any kind, whether it's a rock or a manufactured ruler made of wood or metal, is so strong that these are completely exempt from the cosmic acceleration. So on all these small scales where other forces are operating, we don't expect things to expand or accelerate in their expansion.
All right, the next question is from Kushal, who's on with us live. And they ask, what fluid is expected to be present at the cores of neutron stars, and what role does it play in the magnetic field?
So neutron stars are technically not a fluid. I mean, they have a superfluid characteristic, but neutron star material is essentially pure nuclear material. So it's sort of not, it's not really a good word to use fluid, because fluid we think of as liquid. What is appropriate about the term fluid is it can imply that the particles move around and are not locked in a lattice or rigid. And that's definitely true of a neutron star. So the neutron material in a neutron star is able to move around or circulate. It's a high density situation, of course, like nuclear matter. The star is rotating very rapidly, and that's instabilities associated with the rapid rotation are part of what lets the neutrons move around. So physicists do treat neutron star material as a superfluid material with some ability to move and react to stresses and so on, not a rigid subject matter, because then neutron stars would just shatter if that were the case. So it's a very interesting state of matter, one that, of course, we cannot simulate in the lab, so it's a purely theoretical description that we have at the moment.
All right, our next question is from Tom, who asks, is space expanding? Oh, I'm sorry, I just asked that one. The next one is from Rami, who asks, is there any method to test things like the cosmological constant or the size of the universe?
Testing the cosmological constant is being done at the moment as well as we can. The cosmological constant was a term that Einstein added to the solutions of general relativity to, in his mind, at his time, to stop the universe from being dynamic. He thought, based on talking to astronomers at the time, this was before Hubble, that the universe was static, not changing. And in general relativity, to make the universe static, you actually have to have a cosmological constant. Well, mathematically, this constant has the same effect as dark energy. It will cause an accelerating expansion and acts in opposition to gravity. In Einstein's formulation of this constant, it was truly a constant of nature, which is to say the strength of this repulsive force did not vary with time or with place in the universe. And so that's something astronomers are trying to check. We, of course, see galaxies moving away from us faster and faster. That's the accelerating expansion from our particular perspective. But there are clever experiments done with large surveys that can look back in cosmic time that can test whether the accelerating expansion was different in its nature a few billion years ago. And obviously, we can do surveys in different directions of the sky to see if the accelerating expansion looks the same in different regions of the sky. And so far, both of those experiments indicate that Einstein's cosmological constant is an appropriate description of dark energy, that it doesn't vary with time and it doesn't vary over space. In a sense, that's a little disappointing, because if it did vary with time and it varied in direction in the sky, then we'd have a very interesting handle on what dark energy was.
Our next question from a live viewer is, how long does a supernova remnant live?
Well, a supernova remnant, can persist for a very long time. The more relevant question for an astronomer is, how long can you see a supernova remnant after the explosion? And the answer is, it's not a simple one number answer, because as the shell of very rapidly moving material leaves the side of the supernova and it hits the ambient medium, it shock heats to incredible temperatures, millions of Kelvin, which is why supernova remnants are seen in X-rays, like the Crab Nebula, for example. and other supernova remnants. So at that point, the supernova remnant could be hundreds or thousands of years old, and Crab Nebula is a 1,000-year-old supernova. If you calculate what to expect, then definitely there are supernovas that went off 10,000, maybe 50 or 100,000 years ago, where we might expect to see enough energy left being deposited into the external medium that we could detect it with an X-ray telescope or an optical telescope, glowing gas. So the supernova remnants certainly are visible and persistent for at least tens of thousands of years. At some point, at some longer time scale, the evidence of the supernova sort of gets eradicated. And that's because the star was sitting in a galaxy where the star orbits and the disk of the galaxy are moving at different speeds. So the galaxy, the structures in the galaxy get sort of disrupted or eradicated on some time scale. So if a very old supernova, you just see no evidence, the coherence of that sphere of expanding plasma would essentially be lost as the material moves around, and the material moves at different speeds and different distances from the center of the Milky Way and so on.
Our next live question from Jane, who's on with us, asks, what is the space in between planets and stars made of?
So the space in between planets and stars is an almost perfect vacuum, but not completely vacuum. For instance, in the solar system, there are tiny interplanetary particles, dust particles, and in fact, some of them are not so tiny, and they're all moving very fast. So they actually represent a hazard to spacecraft that we send into the outer solar system, to the spacecraft themselves or to their solar panels, being peppered by tiny impacts. So there's a small gruel, if you like, of particles left over from the formation of the solar system, sort of micrometeorites, if you want to think of them that way. But it's a very, very low density. I mean, it's billions and billions of times less than the density of the Earth's atmosphere, for example. It's still an almost perfect vacuum. Between stars, the vacuum is even better because most of the material that forms stars collapses into the star and attendant planets, and really there's very little left over. So between stars, the density of interstellar space is roughly 1 to 10 hydrogen atoms per cubic centimeter. Hydrogen atom essentially being a proton, possibly with surrounding electron, but the hydrogen may be hot, so just a proton. So one hydrogen atom in a cubic centimeter is an incredibly good vacuum. That's a billion times less hydrogen atoms than in the air. The air is nitrogen and oxygen, but less atoms than the density of air by an incredible factor. So it's an almost perfect vacuum.
Our next question from a live viewer is, a recent Apogee research paper argues that there are no more than 3+1 dimensions. What would that mean for string theory?
If there's a way to prove that there are only 3 spatial and 1 time dimension, which is, of course, the standard formulation of general relativity and special relativity, then yes, that would be a sort of death knell to most string theories, because string theories hypothesize as a way of unifying the 4 forces of nature, hidden dimensions, where some of the correlations and interactions between different forces are sort of concealed from us in a higher dimension and corresponding to a very, very high energy. So if there were a way to prove that space-time was the simple space-time of 3+1, yes, it'd be bad news for string theory. I don't think that that's actually been proven, because refuting something like the supposition of hidden dimensions or compactified spaces is actually really hard to do. And the reason it's hard to do is because string theory predicts that these extra dimensions or hidden dimensions are only manifested on incredibly small scales and or on incredibly high energy scales, far beyond anything we can access with lab technology. So I don't actually think there have been experiments good enough to disprove hidden dimensions yet.
All right, our next question is from a live viewer who asks, since we know that energy never disappears and sound is a kind of energy, Do our voices still rebound in our or a parallel universe?
Yeah, conservation of energy is a pretty good principle in physics. We haven't really found exceptions to it in the terrestrial world or in the lab. And so, yeah, sound waves, they obviously dilute as they travel out into 3 dimensions. They're compression waves, essentially, of the air molecules. And as those compression waves spread out in 3 dimensions, they become much, much weaker with distance. And so that's why sounds are hard to hear from far away. And what happens? Well, in principle, the energy does not disappear. It's just diluting. It's just migrating out from a source at the speed of sound, of course. And at some point, what happens is the strength of that compression wave caused by a voice or a thunderclap or a musical instrument or whatever it might be is diluted to the point where it rivals the natural motions of molecules in the air itself. And at that point, it becomes fundamentally undetectable because you're losing your signal of the sound against the noise caused by just inevitable thermal motions of molecules.
Our next question from a live viewer is from Bernie, who asks, have we ever observed 2 black holes merging? And if so, what does it show us?
Yes, until 2016, the answer would have been no. But in 2016, LIGO, the Laser Interferometric Gravitational Observatory, detected gravitational waves for the first time, and since has found another 4 events. And these events are almost certainly, I mean, essentially beyond reasonable doubt, caused by the merger of distant black holes, because the signature of merging black holes is a pulse of gravitational waves that propagates out through the universe. And LIGO detected initially 1 and then a handful of more events that had this very characteristic trace of merging black holes. Again, we can predict and explain this with simulations now. So these detections were exciting because they showed that black holes merged and that gravity waves exist, a prediction of general relativity, but they also showed really beyond any doubt that black holes exist too, because whatever doubts there may have been about individual isolated black holes, the signature in LIGO was impossible to explain without hypothesizing merging black holes. And we expect when LIGO's in full routine operation at its eventual sensitivity that these merging black holes will be detected about once a week.
The next question is, how can the cosmic microwave background reach us, and why isn't it beyond our cosmic horizon?
So the microwave background doesn't have to reach us because it's already here. It's all around us. So remember that the microwave background is the thermal radiation. It's the radiation left over from the Big Bang, diluted by the expansion of space-time itself. And since the Big Bang was the formation event of the entire universe, this radiation permeates the entire universe. So the radiation left over from the Big Bang is everywhere. It's in principle around the Earth and in the solar system, throughout the galaxy, throughout all the other galaxies. And so the microwave radiation isn't coming from anywhere and it isn't going anywhere. It was ambient relic radiation in expanding space-time, just gradually cooling and lengthening its wavelength. And so we can see it in any direction we look. Those are the maps we've seen of microwaves taken by ground-based telescopes and satellites. And again, it isn't going anywhere. It's just photons traveling at the speed of light through expanding space-time.
The next question is from Kareem, who asks, Einstein's relativity tells us that gravity warps space-time and bends the shape of the universe, which determines the path that objects travel. How does this translate to small objects on Earth, like us or an apple?
Mm-hmm. So, right, the question is alluding to the very, very elegant phrase that John Wheeler had. John Wheeler is the physicist who worked most of his life at the University of Texas, who coined the term black holes in the mid-1960s. And Wheeler says mass, his clever way of summarizing general relativity was that mass tells space had a curve, and curved space tells mass how to move. So these two things are interrelated. And so a black hole is an extreme version of this, where the space-time is actually pinched off from the rest of the universe, and so radiation can't escape and objects can't escape. Something like the Earth going around the sun or the moon going around the Earth is just a much milder version of this scenario. But again, in principle, the space-time is curved by the presence of mass or energy. And so even in a situation like the Earth and the sun, there's curvature of space-time, and that curvature is predicted by general relativity. It's small, it's a very subtle curvature, and it explains the orbit. The orbit is, again, the object in consideration, whether it's the moon going around the Earth or the Earth going around the sun. It's the object responding to the subtle curvature of space-time, caused by the more massive object. And proof that space-time is curved in sort of weak gravity situations like the solar system is the deflection of starlight, gravitational lensing. That was actually first detected caused by the sun in 1919. It was a confirmation of general relativity within a couple of years of the theory being published, and since then that experiment has been verified a number of times. So it's a very subtle deflection. So the curvature is very subtle, but it's real, and it is the explanation in general relativity for why orbits occur in general.
All right, the next question from a live viewer is, in what bands of the electromagnetic spectrum do neutron stars and neutron star binaries emit?
Well, it depends. So isolated neutron stars, completely isolated, could be totally dark. They need not have any electromagnetic radiation. So for instance, we pretty much know from statistics of star evolution and death that there are a few tens of millions of neutron stars in the Milky Way galaxy, and the vast majority of them, we don't know where they are. We don't see any radiation from them, and they're probably undetectable. For some small subset of neutron stars, imperfections in the surface and glitches in the surface or hotspots in the surface allow for the acceleration of particles and low energy radiation to be produced, radio waves. Cyclotron radiation is polarized. And then when the radiation from that hotspot sweeps across the Earth, because the neutron star is spinning quickly, you see a pulse of radio waves. And so that's how neutron stars were detected for the first time. But it's important to remember the pulsars, the way neutron stars were detected for the first time in 1967, reflect probably a tiny fraction of all the neutron stars, most of which don't have the hotspots or the imperfections that let us see them in radio waves. A couple of neutron stars also have optical radiation, so the radiation gets higher energy than radio waves, but that's very rare. The Crab pulsar is one of those situations, but it's very rare. I think only 3 pulsars have shown optical radiation, and there are thousands of pulsars that are only emitting radio waves. And most neutron stars, of course, are emitting nothing. Now, binaries is a different matter. So when binary neutron stars were modeled or hypothesized, it was clear that the collision of neutron stars could accelerate matter to very high energies, relativistic speeds. And so predicted from theory and then observed actually in the last couple of years, again by the gravitational wave experiments, neutron star collisions and mergers do occur, and they generate large amounts of energy, supernova level or even higher, because of the incredible acceleration of particles. They also generate fusion, rapid fusion that will create much or most of the heavy elements in the universe. So these are very important astronomical events.
All right, the next question is, what is the energy source for the electromagnetic radiation that hits the Earth from the sun? Is fusion the sole source? Does it result in the whole electromagnetic spectrum, and how?
The sole source is fusion. So the sun is a nuclear reactor and is converting hydrogen to helium in this 3-step process called the proton-proton chain. And so essentially 0.4% of the mass of a proton is liberated as energy in the fusion reaction. And that energy at the place where the fusion occurs in the center of the sun is temperatures of 10 to 15 million Kelvin. So those first energy released from the sun is X-rays deep in the core, the invisible core, because we can't see to the center of the sun. That radiation bounces its way out and takes thousands of years actually to get to what we see as the surface. And then by then it's cooled and stretched in wavelength to visible light. And so then the visible light reaches us. So the visible light from the sun is just the degraded, much higher energy radiation from the core of the sun where the fusion reactions are actually occurring. So the sun, and then in the atmosphere of the sun and the outer atmosphere of the sun, in a physics is not still fully understood, but it's associated with magnetic fields, acceleration of particles. The corona of the sun, which is a very thin diffuse plasma, is also at a temperature of a few million Kelvin, and that emits X-rays too. So we see the sun in X-rays from its extended corona. So the sun emits a lot of X-rays in the outer parts. It emits visible light, of course, which is the degraded fusion power from its core. And that's about it. The sun doesn't emit large amounts of radio waves or long wavelength radiation at all.
All right, our next question from a live viewer is, what does the double slit experiment tell us about matter? If particles can be at two places at the same time, does it suggest another method of faster than light speed travel?
So the two-slit experiment is foundational in physics. It's Thomas Young. It's about 1800, so it's over 200-year-old experiment. Historically, before Young's experiment, the theory of light that dominated was Newton's theory, and Newton had a corpuscular theory, as it was called. But basically, Newton believed light was a particle, and that's how he thought of light, and he wrote about it. He didn't have any proof or evidence. That's just how he thought about it. When because light clearly carries energy and momentum, and so it made sense to think of it as a tiny little bullets traveling through space. Young's experiment of two slits and the interference that results was only explicable in terms of wave theory of light. And so from the time of Young's experiment, physicists had to acknowledge that light was a wave. The trouble is these truths coexisted. And early in the 20th century, Einstein showed with his explanation of the photoelectric effect that light did indeed have to still be thought of as a particle, a photon. And so as the quantum revolution happened in the 1920s and 30s, physicists had to build theories of nature that acknowledged light as having this dual nature of being both a wave and a particle. In some circumstances, in some experiments, it manifests its particle-like behavior of being discrete and isolated in space, carrying energy and momentum. And in some experiments, it manifests its wave-like nature and the phenomena of waves like diffraction and interference. And both are true. And that is a puzzle. It's not a paradox necessarily. It's just a duality, a twin truth that is still present in physics 100 years later.
All right, the next question from a live viewer is, how is our current idea of space-time different from the historical ether?
So that's a good question. Ether was a hypothesized medium that pervaded space beyond the Earth. And the original idea of ether came from the Greeks. In fact, they had their four elements, earth, air, fire, and water, and they actually hypothesized a fifth element, quintessence. That's from that Latin root for the fifth, number 5. So that fifth element was the ethereal medium through which, that pervaded space, because the Greeks couldn't really imagine nothing. So the idea of a pure vacuum that could hold objects didn't make sense. So they preferred to think of a medium. By the time of the early 20th century, this idea of an ether was still there because people were worrying about light traveling through a vacuum. Well, what was light oscillating and vibrating in? How can you have an oscillation and a vibration in nothing? So it seemed easier to hypothesize an invisible medium called an ether. Also, the relative motions of objects. If the Earth is moving around the sun moving around the galaxy, what is the reference frame for all motions? You have to somehow define a 0 point or a reference for motions. And so the ether helped you do that. And also, light had a speed. It was measured by the beginning of the 20th century very accurately to be 300,000 kilometers per second. And so it seemed like there should be a reference for that speed of traveling of light through this medium, the ether, out in space. The trouble was that the Michelson-Morley experiment in 1905 definitively showed that there is no ether. There is no invisible medium. Light travels at 300,000 kilometers per second regardless of the motion of the source of light, which is a very puzzling result leading to special relativity. So the ether was refuted by experiment in about 100 years ago. And that refutation was the key to the thinking of Einstein that led to the special theory of relativity, which had some very strange concepts of time and space being flexible and distortable, and all premised on the speed of light being a universal constant.
And so this needs a little bit of prefacing. With regards to gravity and relativity in black holes, we often hear the terms tensor and metric. What is a tensor and what is a metric?
So in general relativity, these are part of the baggage of general relativity. That's just physics theory baggage. A tensor essentially is a force that has to be defined in, or can take different strengths in different directions. Generally, we think of a force as something that has a magnitude in a direction, sort of like a vector. Well, a tensor is a sort of more generalized concept than a vector. It talks about the strength of something that can vary both with position and direction. And so you need more quantities to fully specify that force, say gravity force. So a tensor theory of gravity acknowledges that gravity has to be defined at every region in space and in every direction, and that it can take differences in those different regions of space or dimensions and directions. The metric is the mathematical description of the space-time itself. And the simplest way of thinking of a metric is it's the mathematical description of how the space-time might be curved, for example. Because in Newtonian gravity and Euclidean space, there's no curvature, so there's nothing to talk about. Space is just uniform and absolute and linear, and that's really simple to describe. In general relativity, none of those things are true, and so you need a metric, a mathematical description of the potential curvature of space-time and the coupling of space and time to describe the theory. So we have metrics in general relativity, and tensors are the tools to calculate in general relativity.
All right, our next question comes from a live viewer who asks, what processes explain the creation of heavy elements in the cosmos?
Well, the creation of the lower tier heavy elements comes from stars like the sun, but actually including stars more massive than the sun. So the fusion reactions that we see in the sun creating helium at higher temperatures can go on to make carbon, nitrogen, oxygen, and essentially all the elements up to iron. And so we think that all those elements beyond hydrogen and helium was created in the Big Bang, in fact, are coming from stars. It's a more massive star than the sun typically. Beyond that, the fusion source for heavy elements doesn't work because iron's the most stable nucleus. And so while you get energy out by combining nuclei to go towards iron, to go beyond iron, it requires energy. And so essentially in stars, that it stalls at iron. There's no way to go beyond. And so beyond iron, extra energy is needed and the extra mechanism is needed. And the two mechanisms that we know of that can add the energy to take you all the way through the periodic table and create the gold, silver, platinum, uranium, plutonium, every element in the periodic table are supernova explosions. So the catastrophic collapse of a star once the last fusion reaction occurs, and then the conversion of that gravitational potential energy into a incredibly high energy blast wave where explosive nucleosynthesis occurs at temperatures of a few billion Kelvin. And those blast waves are definitely able to make heavy elements. However, just in the last few years, it's emerged that the single biggest source of those heavy elements beyond iron is not supernova, because the yield of heavy elements in the models and simulations has always been a little too low for what we observe. The more efficient and abundant source of heavy elements is neutron star collisions and mergers. Because when neutron stars emerge and collide, the neutrons are accelerated to extremely high velocities, and those neutrons can penetrate an existing atomic nucleus, because there's no electrical repulsion, and ratchet it up by an atomic number. Remember that you can make neutron, a free neutron will decay into a proton, electron, and will decay into a proton, a positron, and an antineutrino. And so you can go ratchet up the periodic table by neutron star collisions because of the vast number of neutrons that are accelerated. And the theories of those collisions suggest that the majority of the heavy elements in the universe come from that mechanism.
All right, I think we're going to take 2 more questions before we end. The next question from our live viewer is, given that there is no matter in interstellar space and temperature has basically no meaning, would an unprotected human body placed in intergalactic space feel cold? Would we die by radiating out heat but stay alive for hours?
Unfortunately, no. Like you wouldn't last long at all. So people have done this. It doesn't actually matter whether you pick intergalactic, interstellar, or interplanetary space. And people have sort of worked this out actually within the solar system. Like what happens if an astronaut somehow is unprotected? The spacesuit ruptures or the space station ruptures and they're ejected into the vacuum of space. It's pretty much the same outcome regardless of which type of vacuum you're talking about. And the unfortunate truth is that while it is cold out there, it's actually 3 degrees Kelvin because all there is the microwave background radiation. So it's almost perfectly cold. It's not actually initially the cold that kills you. It's the vacuum itself. So the human body is, of course, a bag of water essentially kept intact by the skin, and the vacuum of space means that the human body will try and cool, of course, but it'll also try and expand, and that expanding will also act to cool, and the blood will boil, and so because it's sort of evaporating, not because it's boiling because it's hot, but just boiling because of the lower density. And so it's actually a pretty ugly death in the vacuum of space. And the internal heat of the human body will not keep a human alive. That's the standard calculation for how long you would exist if you were suddenly in the vacuum of space is something like 10 or 15 seconds before you pass out, black out, and your brain function ceases.
All right, and our final question for our live session today is from one of our online viewers who asks, what is the proper motion of stars? Does proper motion imply that stars are in fact not stationary as we have been taught in schools?
Yeah, I'm glad we didn't finish with the hideous death in the vacuum. Proper motion is, yes, stars are not stationary. When you see stars in the sky and when you map the sky, the night sky from one year to the next, there's almost no change. However, if you map the sky with telescopes from year to year, or from decade to decade in particular, the stars are moving. And so people have now done surveys that show very clearly that stars are in motion across the sky. It's very small, it's very subtle. You never see it with your eye. You need a careful CCD camera and a deep detector and a careful grid overlay to see the motion. So stars are moving across the sky because that's all you see. And then if you measure the Doppler shift by spectroscopy, that tells you about the to and fro motion, the motion towards or away from the Earth and the sun. And so we can see that stars are moving that way too. And so we think stars are moving at few to tens of kilometers per second in the neighborhood of the sun. We can measure the to and fro motion by the Doppler shift. We can measure the transverse motion on the sky by careful surveys year after year and measuring positions very accurately. And you can combine those two, the transverse and the line of sight motion, to get a space velocity. And so those velocities have been measured, even a few decades ago, they'd been measured for dozens of stars. And now with much better instruments in space and space telescopes, they've been measured now for thousands of stars. In fact, the Gaia mission is measuring the motions, the transverse motions of tens of millions of stars in the Milky Way. So yes, stars are moving. They're just milling around by gravity within the general rotation of the Milky Way, and we can detect that. So that's great. excellent questions as always, and thanks for your questions, and thanks to our crew here who helped gather all this information. We put it online on YouTube, and you can catch it again there if you didn't catch it this time. Thank you.